Alright, so in our last video we got our first introduction into a geometric representation of vectors. And we did that in R2 because R2 is really the easiest dimensional space to visualize in. There is one more dimensional space that we can visualize in, and that is R3. Now, it's a lot harder to visualize in R3. Unfortunately, it's a lot harder to draw in R3, but we can give it our best shot. And so I'm going to go ahead and do that. Now, before I try to attempt to draw this vector v, the important thing to note is that unlike vectors in R2, we have an additional entry, right? And so when we were going over vector basics and we were introducing it, I had mentioned that these entries have a meaning, right? Each entry corresponds to a different variable, a different dimension, a place in a different dimension, right? So I'll go ahead and try to draw this vector right here, and like I said, I'm going to give it my best shot, no promises. So it's going to kind of be something like this. I'll do it a little better than that, but something kind of like that. Oops. All right, put the little arrow. All right, and for me, sometimes it helps to kind of visualize the three-dimensional vectors by drawing some lines to them. So, I mean, this is kind of like this right here. Right? Okay, now this guy is a little tougher. Is a little tougher to draw to. All right, that's from the third entry, right? So that's down one, and then here's from that first entry. We'll call that over 2. This isn't exactly drawn to scale again. This is pretty tough to draw, so cut me a little slack here. But basically, what we're looking at, right, is let's say this is x, this is y, and this is z. So that kind of roughly corresponds to x, y, and z. And you may have a different convention depending on what class you're in, physics, or what your Calc 3 teacher, if you've taken that course, decided to do as far as creating these dimensional spaces or these dimensional axes in 3 dimensions to visualize different types of things. But we'll go ahead and use that as our dimensional axes. So that's R3, right? Really, again, just denoted with that. But what about past R3, right? There's so many dimensions that we can go to. So let's talk about that a little bit. So what's after R3? Well, you might see the pattern here and understanding that, okay, well, we're just really increasing the number that we have this real number symbol raised to. And it's not supposed to be thought of as an exponent, so don't think about it like that. When I say the term raised, it's just more of a placeholder. But what we really have is we have what we call Rn, where n is, I'll go ahead and just say n is some positive number. Okay? And what that equates to as far as vectors go is something that looks like this. So I'll define a new vector. I'll call it Q. Okay? And what we have here is, you can see we have a vector that we're used to, right, with a couple entries in the beginning, and then give it a ways to go, right? We have a little dot notation, and you can see the final entry is going to be Qn. So that final entry is defined by whatever space you're in, right? When we were in 3-dimensional space, we had 3 entries, we had 3 elements. When we were in 2-dimensional space, we had 2 entries, 2 elements. And Rn, when we were in n-dimensional space, we have n elements, or n entries. And this is really just an abstraction that we use. This is what we use in linear algebra to talk about just any dimensional space. N can be 5, it could be 500. It doesn't matter, right? And the cool thing about Rn is that the same rules apply to Rn that applied in R2. So let's talk about those a little bit. So those basic properties that we went over, that we went over in our first introduction to vectors still apply here. So what was one of those? That was, one of them was scalar multiplication. And if you forget what that was really just taking some constant number, some real number, c, and multiplying it by a vector. And I'll go ahead and use q just so we're kind of being consistent with this n-dimensional space idea, right? So we can take any constant c, right, any real number, since we're dealing in the real number plane, in a real number space, any real number, and multiply it by our vector, and we can just push that through to each corresponding element, like we saw in the first video. So what are the other properties that we learned? We learned about addition, right? So let's say we had a vector q plus a vector m, right? Well, that is just equal to q1 plus m1, right? The element-wise addition of these two vectors. Okay, so we can see that the same things that are happening in R2 are happening in Rn, are happening in really any dimensional space that we can think of, that we can represent with vectors. And then finally, the last one we kind of touched on briefly was equality. And that's just saying two vectors are equal. So let's say two vectors are really just equal when they're element-wise equivalent. So when each element is the same thing, right? So I could say, let's say we have q, let's say we have n, all right, and that's equal to 1, 2, we have a bunch of entries, and then 4, okay? This is still an n-dimensional space, all right? Don't get confused. And then we have a vector L, and we have 1, 2, 4. Now, you just have to trust me when I say that the dots would be equal, and if they were, then these two vectors, n and L, would also be equal to one another. One last thing I want to talk about before we end the video is a special kind of vector called the zero vector. And the zero vector shows up a lot, actually. It plays a pretty important role in a lot of linear algebra. It allows us to do a lot of really important things. Now, the zero vector, as you might have guessed, is really, it's a vector in any dimensional space, okay? So we could be in R2, and it's just going to be two zeros, all right? And it's represented in a dimensional space by the point on the origin, all right? So this is the zero vector. This you might see with a very bold-faced type, bold-faced font, or you might see it with a arrow on the top, like I was mentioning in an earlier video, to denote that it is a vector. So this is in R2. As you might have guessed, in R3 we just have 3 zeros. Right? So this is also equal to the zero vector in R3. All right, and then finally we have one. I'll just denote this as the nth entry. This is also the zero vector. So as you might have been able to pick up, really, the zero vector is present in all of these spaces, in all of these dimensional spaces in Rn. Okay, and again, it's a special vector that you'll see more and more as we move along, and plays an important role in what we can do in linear algebra.